Hi there. So now that we've looked at a data set involving a mean, we did some bootstrapping, let's go to the theoretical side, and we want to make a theoretical confidence interval for a mean. But before we do that, we need to review sampling distributions, okay? So that's how we get the model that we're basing our theoretical formula on, right? This theoretical model. So in order to do this, we pretend to know what a population is, right? We pretend to know the population mean and standard deviation, and then we take repeated samples of a mean for many, many random samples of the same size, and we see what happens, right? So we've done this, we've reviewed this for proportions, but let's go ahead and do it for means. So, and we've seen this in our simulations too. So if you take many, many random samples of the same size from the same population for a particular statistic, so here we're looking at a mean, we get a normal distribution, as long as certain conditions are met. Okay, so we're going to talk about those. And what we've seen is the mean stays the same, meaning same as the population mean, but the standard error gets smaller the larger the sample size. So we have a certain standard deviation of our population, but because we're taking a random sample and averaging, everything comes into the middle. So our sample to sample variation is smaller. Let's make a note of that. Our sample to sample variation is smaller than for individual to individual. Okay, that's a lot to write out, individual to individual. Okay, and then of course the larger sample size we take, so we could take a sample of 100 people. If we did 500 people, we're averaging more, and so it will go even more into the middle. So the larger the sample size, the smaller the standard error. Okay, so we can kind of review this central limit theorem, conditions and model for a mean, x bar. So we have certain conditions that need to be met. Let me go one by one. So whenever we're using a theoretical model, we need to check the conditions or assumptions to ensure the model applies to the situation. So we need to make sure we get that normal curve before we use the Staplett normal calculator or any normal calculator. Okay, so the first three are going to be the same as for proportion, so you'll be pretty familiar with those, okay? Independence. The individuals or items must be independent of each other regarding the variable measured, so we'll always state that variable measured. Randomization, the samples need to be randomly chosen, or it's not safe to assume independence. Large population, if sampling without replacement, we must be sampling from a large population to consider the individuals independent of each other. This is the small M&M bag versus the large M&M bag. If you're sampling from a too small population, then just taking one out will greatly affect the probabilities, versus if you have a large population, taking one out doesn't make much difference. Okay, so sometimes this is called the 10% condition, or we've been calling it the large population. The population must be at least 10 times our sample size. Okay, so these first three are the same as for proportions, okay? But the way we do the sample size is different. You might remember we did success failure before because the normal shape depended on n and p. Here we don't have a p, we have an n. So this one is called sample size. And there's a few different ways that this can happen. So either if we feel like the population is normal, so measurements do tend to produce a normal distribution. They just tend to be normally distributed. So if we believe the population is normal, or if we're told the population is normal, then that's great, because remember, once it's normal, it's always normal. Or we can check our sample. We check that our sample is nearly normal. It won't be perfect, but we can check that it looks roughly normal. Or if n is greater than or equal to 30. Okay, so 3 different ways we could meet this one. Now, if there are outliers or a strong skew, we cannot use this method. Okay, so what we're going to do is we're going to check the histogram and box plot with our sample. So if we don't know that our population is normal and we don't have n greater than 30, we're going to check our histogram and box plot to find out if it's nearly normal. Okay, let me just also highlight, if there are outliers or a strong skew, we cannot use this method. Okay, great. So those are our conditions. When those conditions are met, then this is the model we have, and this might look familiar from, hopefully, from 243. When the conditions are met, the sampling distribution for the mean is modeled by a normal distribution with the following parameters. So we have our x bar is distributed as normal. The first thing is the mean. The second input into a normal distribution is either standard error or standard deviation. Here we're talking about standard error because we're talking about repeated random samples and sample to sample variation. Let me see, I don't have that written down. So sample to sample. Okay, so this is giving us the formula we're going to use for our standard error and for our mean. So remember, this is when we are pretending to know the population, so we know mu and sigma. In practice, we will not know those. Okay, another note here. It's kind of interesting, the difference between means and proportions. For means, there are 2 unknowns, right? For proportion, you just have the proportion that's unknown. But for means, we don't know the population mean, and we also generally don't know the standard deviation, right? So this increases the variation. There's 2 things we don't know now. This increases the variation. So if we did know the population standard deviation, if we know the population standard deviation or have a large sample size, we can use this normal distribution. But that's unrealistic in practice. Like, why would we know the population standard deviation if we don't know the mean? So it's pretty rare to know that. So, and often we are using small sample sizes. So for this reason, we need to use a different distribution. Okay, so if sigma is known, and in some statistics classes we'll do these problems where you do use a normal for a mean if sigma is known, right? But we're not going to be using that case because I don't think it's very realistic. So we're going to use the t distribution. So you're going to learn about the t distribution. Okay, now this is why we're using the t distribution, because there's it doesn't work well for small sample sizes because we have this extra variation. The t distribution is also called the student's t distribution. It works better for small sample sizes. So I'll show you more about the t in just a moment, but first I want to show you the steps for a theoretical confidence interval. Then I'll show you more about the t. Okay, and we are assuming, so this is sigma unknown. If you were comparing this to other videos, if sigma is known, you can use the normal, but we are not going to do that case, okay? So this is steps for a theoretical confidence interval for a mean, and also in GeoGebra is called t-estimate of a mean. Okay, so our steps are calculate the point estimate, right? So that's the best estimate or point estimate that we talked about in the last video. That's going to be x bar. And find the critical t value, t star, for the confidence level using degrees of freedom n-1. Okay, so we'll learn how to find this critical t value. It's similar to when we did the critical z values for proportions. Okay, then we're going to check the conditions, and those are the four things: independence, randomization, large population, and sample size. Okay, now we have our formula: x bar plus or minus t star sub n minus 1 times s over square root of n. Okay, so we'll break this formula down here. Essentially, we're doing x bar plus or minus the margin of error, right? That's our general confidence interval. We have our estimate, our point estimate, and we add and subtract the margin of error, right? Now, the margin of error is a certain number of standard errors that we go out, okay? And then we need to select a certain number of standard errors to go out based on our confidence level. Do we want the middle 90%, 95%, 99%, or something else? Okay, so another way we could write our confidence interval is x bar plus or minus t star times the standard error, right? That's a certain number of standard errors. And the critical t value, which before was a critical z value, critical t value is the number of standard errors we need to go out to get that percentage confidence level. Okay? And also, so you can see our standard error is coming from this model right up above, sigma over square root of n, but I'm using the s instead because we don't know sigma, so we have to estimate it with the sample standard deviation. Okay, and then divide by square root of n, and then I also just put a subscript to remind us that we have to use the degrees of freedom for the t distribution, and that is n minus 1. So I'll show you how that works pretty soon. Okay, so we've got our formula. Then, of course, we always write our interpretation in context. Write the interpretation in context. Okay, and let's see, what is this note here? Okay, this is kind of what I wrote on the side. The standard error is given by this, s over square root of n. And the margin of error is the t star times. Okay, so I have these other two formulas built in here if you want just one of those formulas, but ideally I hope you recognize all the parts of the confidence interval. Okay, let me check what's on the next page. Yes, okay, so at the very top of the next page is the question, why do we need a new distribution? Why do we need this t distribution? And so I have found a great video where someone else explains the history of that. So I'm going to have you go to that video next, and then I will pick up with you on looking at the t distribution in Staplet. Okay, so I'll see you in the next couple videos.